Good afternoon, and welcome to Research in Action, presented to you by the Division of Research at Florida Atlantic University. Before we get started, I would like to go over a few housekeeping items here. My name is Karen Scapinato. I work in the Division of Research and will be the moderator today. Because of the number of attendees we typically have at our Research in Action series, we won't allow audio questions. However, we would like to address your questions. So if you hover your mouse in the bottom of your screen here, you see a Q&A button. If you push that, you can type your question. And at the end of the presentation, we will go over as many questions as we can in the allotted time. We will collect the remaining questions, if there are any, and address those on our website, in the Research in Action website. With that, it is my great pleasure to introduce Dr. Lawrence Toll. Dr. Toll received his Ph.D. in biological chemistry at UCLA and then did a postdoc at Johns Hopkins University. He spent a number of years in various different labs, including at the Institut Pasteur in Paris, and as well as in Strasbourg. Most recently, he was at the Torrey Pines Institute before he came to join FAU here in the Department of Biomedical Science. Dr. Toll's interest is in opioids and pain, and he is very interested in researching and identifying new drug targets that lead to new drug development of those drugs that do not cause addiction. With that, I'm going to turn it over to Dr. Toll. Welcome, Dr. Toll.
Hi, thank you, Karen. It's a pleasure to be here. You know, this talk was originally supposed to be at the library in Boca Raton, but as all hell is broken loose in the world, we can't do that anymore. So I'm in the comfort of my own office. I hope it works out. It's not as much fun for me because I can't see all of your smiling faces out there. Or even more importantly, I can't see your quizzical look when you're wondering what the hell I'm talking about. But I will do my best to try to be coherent and hopefully tell you a little bit about opioids and a little bit about what we're doing about it. I'm ready to go. Should I start my screen? Karen, can I do this? Yeah, screen share. Okay, that looks like it. Anyway, so I'm going to talk about opiates today, and I thought I'd start out, that's not it. Let's go here to PowerPoint. There we go. That worked. So I have been asked in the past if cocaine is the same as morphine or similar to morphine or in the same family as morphine. And the answer is no. Morphine comes from opioid poppies, opium poppies, which are found all over the world. Afghanistan has a lot of them, as you all know. Cocaine comes from the leaves of a coca plant, which is found more in South America, I think. Both have been around and been used for thousands of years. Now, to get opium out of an opium poppy, you take the little bulb there that you can see. I wonder if you can see my, my pointer here. You can see that if you put a slice into the bulb of the poppy, the juice inside, the resin inside is so prevalent, it just seeps out. And you collect this, and that is where the opium comes from. And from this, you can make morphine and the other ingredients from the plant. And on your left here is you see a picture of what morphine is. Now, this doesn't mean much to people who aren't chemists, but it's made up of carbons and hydrogens and a little bit of oxygen, and importantly, a nitrogen there. This was first isolated from the poppy in 1806, and the structure was identified way back in 1847. Now, this is considered an alkaloid. An alkaloid is a small molecule that comes from a plant. And generally alkaloids, I think, are in plants because they're bitter and they keep bugs away. And so that's why morphine and the other things that are prevalent that are found inside this poppy are there in the first place. What I'm showing you on the right is the first attempt at doing some chemistry on morphine itself. And this was done to try to make a non-addicting analgesic. And so from the time when morphine was first used, people found out that it was addicting. It was being used as an analgesic in the 1800s, and it was addicting. And a company that you all know called Bayer, a German company, you know better as Bayer, perhaps, made the first attempt at making a non-addicting analgesic. So this was first synthesized in 1874. It was commercialized in 1898, as I said, by Bayer, the Bayer company. And this compound, as you see there, is heroin. So this is very easy to make from morphine. It's diacetyl morphine. This was purified and synthesized and sold as heroin. So this was from, you can see, from 1901. And this was sold to people in Germany and in the United States and around the world, I guess. And it was used in an analgesic. It was used as a cough suppressant. It was used for all sorts of purposes. And that was because in those days, there was no FDA, you know, and so you could make compounds and try them out in people. And I guess it was a little while before people decided that this was probably not a good idea. So anyway, this was sold, marketed, and in fact, it was sold to babies. This was made for teething for little babies and other cough, other things. So this was a bad choice. And I think over the years, it's become clear that you can't just make something and try it out and see if it works. I'm sure it was analgesic, but it didn't lead to good things in the long run. So right now, opiates are mainly used for pain. At least we used licitly rather than illicitly. And there's very good reasons for this. It's a huge market. 20% of the world is in pain, is in chronic pain. 100 million Americans are in chronic pain. If you're my age, you know that your back hurts. And opiates are the best treatment for moderate and severe pain. The annual cost of chronic pain in the United States is billions of dollars. This includes loss of work and medications and all of the things that are associated with it. But it's a huge problem. It's a huge market. The global market for opioids itself is $20 billion a year. And for analgesics as a whole is $46 billion. Now, I've used the term analgesics before, and people don't know exactly what I mean by that. An analgesic is a painkiller. Now, I want to show that this is separate than a local anesthetic or an anesthetic. An anesthetic is something that numbs you. So, you know, if you go to the dentist, you get a shot of Novocaine, your mouth is numb. And it doesn't hurt, that's good, but your mouth is numb and you go to drink some water and it dribbles down your chin. So that's not the point of an analgesic. An analgesic actually blocks the pain directly without causing numbness of the place that it's given or something like that. So an analgesic is a different thing, that it's more useful in general life than anesthetic. And there's opioid analgesics and there's non-opioid analgesics. And you know, over-the-counter analgesics you take all the time, like an aspirin or ibuprofen. And they work by different mechanisms in opiates, and this is why they're not as effective as opiates, but they can be used for pain that's not so severe. So the overall analgesic market is about twice the amount that is for opiates by themselves. So anyway, it's a very large market. It's very important. And for this reason, it was one of the first type of compounds that were actually chemically modified to look for new molecules that will do similar things. So this is called medicinal chemistry, where you take a particular compound and you modify it to try to get similar but better properties. And this was done very early. As I said, the first one was heroin in the end of the 1800s. But in fact, there's been a lot more chemistry that was been done on this since then. So the chemistry is either semi-synthetic or fully synthetic. So semi-synthetic means you actually start with one of the natural products that come from the opium poppy itself. So there's 3 opiates in the opium poppy. There's morphine, there's codeine, and something called thebaine. Morphine is by far the highest concentration among the 3, but they're all 3 there. And they all have similar structures to this. And so some of the semi-synthetic chemistry comes from either starting with morphine or starting with thebaine and doing chemistry from that. And the other way is fully synthetic, where you just start with smaller molecules and you put them together in a laboratory, and you don't start with morphine itself. So as you can see here, if you look at morphine, and I don't know if you can see my little pointer here, but you see that heroin has a structure very similar to morphine. And in fact, morphine has a structure very similar to morphine as well. And what they did is they took out this oxygen bridge here, and you leave the same backbone as you find with morphine. And in fact, the properties of morphinanes are very similar to opiates. And in fact, they bind at the opioid binding sites in the same way that morphine binds. And so there have been many, many morphinanes that have been made, which have properties similar to morphine and some different. And I'll get into that in a little bit. After the morphinanes were made, what medicinal chemists did is they kept making smaller and smaller versions. So if you take out this ring, now morphine has 1, 2, 3, 4, 5 rings. Morphinanes have 4, 1, 2, 3, and this 4th one, which you can't quite see because it's at an angle. Benzomorphins have 3 rings. So they took out this cyclohexyl ring, and you can make a benzomorphin. And these bind the same way as morphine does, and has similar properties. And you can make many compounds. There have been hundreds and hundreds of benzomorphins that were made as well. The last group here are fentanyls, and you've heard of fentanyl recently. Fentanyl now has basically 2 important rings, and it doesn't really look like a morphine structure anymore, but in fact, this nitrogen here is similar to this nitrogen here, and this ring here is similar to this ring here, and I hope you can see my pointer. But at any rate, it binds with very high affinity to opiate receptors as well, just as morphine does. So it's the good thing about there's good news and bad news about fentanyl. The good news is that it's small, it's easy to make, and it's a very potent compound. In fact, fentanyl itself is about 70 to 100 times more potent than morphine. So you don't need much of it. It's a great analgesic. It works various ways. It's easy to make, and those are all good things. The bad news is that it's small and easy to make. And so that means that it's not only good people who are making it, it's bad people. And it's easy to make in a laboratory anywhere. And fentanyl is now a big problem, as you all know, and I'll talk about it again in a minute. In fact, there's been thousands of fentanyls made as well. And some are super duper potent compounds. There's one called 3-methylfentanyl, which is 100 times more potent than fentanyl itself. And so fentanyl is 100 times morphine. 3-methylfentanyl is 100 times fentanyl. So this compound is 10,000 times more potent than morphine. It's a tiny, tiny bit will kill you. So some of these compounds are super duper dangerous and easy to make, and that's a problem. So I want to talk about for a minute the steps that led up to the opioid epidemic. Now, this is a problem that we're not talking about as much as we were about a year ago, and that's because we're talking about a pandemic instead of an epidemic. But in fact, this hasn't gone away, though in fact, it's better than it was a couple of years ago. But there were many reasons that led to where we end up today and where we were a few years ago. One of the first is that there was concern that patients weren't treated effectively for pain. And this is something that goes up and down, that doctors think, oh, patients aren't treated enough, so we better give them, more morphine, more opiates. And then they thought, oh, they're getting too much opiates, and so the guidelines change. And but for a while, I think about 20 years ago, people were really under administering painkillers, and there were lots of people in the United States and elsewhere in severe pain, and pain became what was called the fifth vital sign. And it was treated as doctors as just as important as your temperature and your blood pressure. And they would always ask, are you in pain? They have model levels of measuring pain, 1 to 10. And so this became very important. And doctors said, oh, we're not treating pain sufficiently. We've got to give more. So that was a start. Then it turned out that, morphine is not given generally orally. Morphine is given in hospitals, IV, or some other route of administration because it's not very active orally. But some companies started making more orally active compounds and also controlled release formulations, like OxyContin is actually the slow release formulation. And this allowed a more widespread use of the drugs. The next thing that happened is that certain companies very, very aggressively marketed these compounds. And I won't name names, you've heard of them in the news, but salesmen would go to the doctor's office and say, this drug is not addicting if you're in pain. So if people aren't in pain, there's no reason you shouldn't be giving plenty of this OxyContin or whatever drug you're giving, Vicodin. Then they would say, these slow release formulations are less addicting than the other types of formulations. And so you don't have to be afraid of these. These are not addicting compounds. And of course, that's not true. And the scene changed, and doctors, instead of giving, a week's supply, all of a sudden are giving a month's supply because it's not going to hurt anyway, and if there's no reason to be in pain. And so you could go to the doctor for a sprained ankle, as a woman who worked with me did with her daughter, and they gave her a 30-day supply of Vicodin. Or, which has happened with me, go to the dentist, I had a root canal, and they gave me a month's supply of Vicodin. So this isn't necessary. Chronic pain lasts a day or 2 days, maybe. If it's really bad, it can last a week. And but all of a sudden, in everybody's house is a 30-day supply of Vicodin or Percocet or OxyContin. And this is a problem. And this was a problem for 2 reasons. Number one, people thought, oh, well, they gave me a month's supply. Maybe I'm supposed to take them all, like you do with antibiotic. Other people didn't take them all, and they just sat there in their medicine cabinets. And what happened with that is that people's grandsons would go into their grandmother's medicine cabinet and find a bottle of OxyContin that wasn't being used. And this led to addiction a lot. And so the amount of these prescription opiates that was used just went crazy. Over time, doctors finally realized that was an issue. There was OxyContin on the streets. There was Vicodin in the hands of kids, and the prescriptions were reduced greatly. And what happened was people couldn't find any more OxyContin or Vicodin. And what people started doing is they returned to heroin because it was cheaper, it's on the street, it was easy to get. And consequently, people who started because they had a back pain and then couldn't get the pills anymore after they're addicted, returned to heroin. Well, this was a problem. And it got to be a bigger problem because some of the drug traffickers realized it was way easier and way cheaper to make fentanyl than it was to make heroin. And so fentanyl was being put into the heroin, and the drug addicts didn't even know what they were taking. And what happens is that fentanyl is 100 times more potent than morphine. It's not only more potent for the rewarding and the analgesic properties, it's got 100 times more respiratory depression, and this is why people were dying. And in fact, if you look on the next slide, what you see are deaths in the United States. The first one on the left is just overdose deaths. You notice that by 2017, 2018, there are 70,000 deaths per year. So this is, we've just now passed it on COVID-19 in a few months, but per year, the annual deaths were very high. And you see went up by fourfold since around the year 2000. If you look on the right, you really see how this happened. This blue line here on the top here, if you can see what I'm pointing at, are prescription opioids. And this is deaths again. So they went from very low, 3,000, 4,000 a year around 2000, up to 15,000 a year in 2010. That was when it started to drop off, that the availability of the prescription opioids were not there. And these numbers started to drop off a little bit. But you can see that if you look at here, this green line is heroin. So this is when heroin picked up because people couldn't get the prescription opiates anymore. But then you see around 2014, fentanyl started getting on the market, and it went from almost zero and just shot up like crazy. And this is because this was being substituted for heroin to the addicts, and they're just dying very, very quickly. So this is really what happened, and this is how we got to where we are today. So we're today with 1 million opiate addicts in the United States, I think. And we got a problem. So first, I want to give you the definition of a drug addiction. This is according to the National Institute on Drug Abuse, which funds my research. And by their definition, addiction is defined as a chronic relapsing disorder characterized by compulsive drug seeking and use despite adverse consequences. So we all know somebody who's gone this route. And the point is that even though you know it's bad for you, you can't stop. And this is a chronic relapsing disorder. You can get better, but it's really hard to make it go away. And the reason it's hard to make it go away is because of the second paragraph I have there. And this is, it actually changes your brain. It changes the chemistry in your brain. It changes the neuronal connections in your brain, and it screws you up in terms of what was rewarding and what is stressful and your self-control, and it lasts for a very long time. If you have ever been a smoker, you know, you can stop smoking, but you want another cigarette even weeks later. And I want to say that this is different than drug dependence. So this is addiction. Addiction means that you want to take the drug. It's a compulsion. Drug dependence is something different. And what that means by definition is that when you stop taking the drug, you will go through withdrawal. So if you stop taking morphine or heroin, you will go through withdrawal. But that doesn't mean you're addicted. In fact, addiction takes some length of time before you get the changes in your brain that really lead to this. And so addiction can take perhaps a year, I've been told, though it depends on the amount you take and the person-to-person characteristics. But if you take opiates for a week or a month, you can stop. And you'll go through with some withdrawal, but you're not going to necessarily be addicted to the thing. But if you take it longer, it's going to be a problem. Now, you know that, for instance, if you're an alcoholic or a smoker, you stop smoking and the withdrawal is not fun. There's anxiety, there's other kinds of things that go on, but withdrawal from opiates is not fun at all. It's very bad. In fact, there's all sorts of problems that you're vomiting and the temperature goes up and all of these, much more than the anxiety and the depression. So the withdrawal from opiates is very, very bad. And it's one of the reasons that people keep taking the drugs. So this is also from NIDA, this picture of a funny picture of a brain. And I do want to mention exactly what's going on in there. I don't know exactly what's going on, but we do know some things that's going on in the brain when taking opioids. And that the opiate pathway is actually considered here. There's a little spot in the back of your brain called the VTA, the ventral tegmental area. And it has these neurons that project to what's called the nucleus accumbens, which is more on the front of your brain. And these neurons contain the neurotransmitter dopamine. And dopamine is what makes the rewarding nature of everything, as far as we can tell. Now, it's much more complicated than that, but we know that dopamine is very important. So dopamine, if you give an opioid, what you get is you get these cells firing, and you get an increase of dopamine in the nucleus accumbens. You can actually measure this with a method called microdialysis, which is shown here on the right. If you take a mouse or a rat, and you can stick a probe down into this nucleus accumbens, and you put artificial cerebrospinal fluid through, what happens is the contents of the brain will get pumped out, and you can put them in a tube, but you can measure it, and you can actually see that if you give morphine, you get an increase in the amount of dopamine in this one particular brain region. And in fact, it's not only morphine that does this. As I said, all rewarding substances do this. So cocaine does it better than morphine does. You get like a 4-fold increase of dopamine instead of a 2-fold increase. Amphetamine was even better and lasts longer. But other things that are important for life do the same, like chocolate. Well, it's not necessarily important for life, but for some people it is. And chocolate causes an increase in dopamine, and sex causes an increase in dopamine. And in fact, feeding causes an increase in dopamine. And so all of these things are important, and this is important to tell you things that you really want to do. The trouble is with drug abuse, of course, is it hijacks this whole pathway and makes it so that there's too much dopamine being released, and you want to continue to be getting this reward. And when you take it away, dopamine is messed up, and other neurotransmitters like opiates are messed up. And this leads to not only the withdrawal that happens right away, but the long-term consequences of drug abuse. So it's much of it is due to this increase in dopamine here in the nucleus accumbens. What am I doing? Okay, so there's ways to treat drug abuse. You can block withdrawal. People have known that a drug called clonidine works, has been around for a very long time and blocks withdrawal, but it doesn't block the drug abuse itself. There's behavioral therapies that people try. They don't work that well. Over time, people generally relapse. And then there's medications. There's methadone, which has been around for 50 years. This is methadone maintenance. So you take methadone for the rest of your life. And the good thing about that is that you can go back and live a normal life that you can't do when you're taking heroin. The problem with heroin, it comes and goes and comes and goes. Methadone has different pharmacokinetics. It lasts a full day. And so you can take a drink of methadone in the morning and you can go about your daily life. The trouble with methadone is you can only get it in methadone clinics. That's changed now with something called buprenorphine, which is another long-lasting drug, but it's slightly different than methadone, and people can take that at home. There's another drug called Suboxone, which is actually a combination of buprenorphine and naloxone. And this is now, I think, one of the prime medications that people take. Another drug that's taken is something called naltrexone, which is an opiate antagonist. It blocks the actions of morphine and other opiates. And Vivitrol is a long-lasting version of that. You can take this and you get a shot. It lasts a month. And when you take naltrexone, the opiates don't work. They don't do anything. So this works great, except for the fact that people don't really like to take it, because opiates are important for your natural reward, and naltrexone doesn't make you feel good. The last drug I have here is naloxone, which is Narcan, which is not generally used for overdose. And if you give it that, it blocks the respiratory depression and people wake up. So why do the people take opiates for pain? And the answer is, pain is complicated. You think of pain as this sensory thing in your arm or your tooth or somewhere. But in fact, there's an emotional or affective component for pain as well. And it turns out that opiates work on both of these. And you can measure these differently. You can measure the sensory aspect of pain with experiments we do in the lab, something called tail flick or hot plate. This is called a Hargraves apparatus, and on top you see a rat. And this thing shines a light, and you can shine a light on the paw or shine a light on the tail, and you can measure the time it takes for the opioid to move, for the animal to move their foot or their tail. And this is the latency. And you know, generally it lasts a few seconds. This is a very easy, benign test. It doesn't hurt because when the animal feels the heat, they move their tail. We do this with graduate students. We do a finger flick, and you put your finger on the light, and when it gets too warm, you move your finger. So from this, you can measure the actions of an analgesic, like morphine. And so if you give a mouse or a rat morphine, they will leave their tail there till it burns. And so we actually have a cutoff. We don't allow that to happen. So opiates block this. And they're in the pain pathways and block the sensory component of pain. But in fact, there's an emotional component as well. And I want to, the way we measure this is with a really interesting experiment called a condition-place preference. In this test, you can take a mouse or a rat and you have a box with two sides, and the two sides are different. And the way you train this animal is in this test, you have an animal in chronic pain, and you put him in one side, and you keep him there for 15 minutes. And then the next day, you take the same animal and you give him an opioid, and you put him on the other side, and you leave him there for 15 minutes. And you do this a few times. And then on the last day, you take out a little door in the middle. You don't give him any drug. You put him inside and you say, go. And you measure the time they spend on each side. And as you can imagine, they spend more time on the side that they are not in pain. Okay? This is an emotional component. We're not blocking any pain in doing this experiment, but they know they feel better in the side that they didn't have the pain. And so opioids also do this. And for this reason, they're very powerful and they're very effective in blocking all aspects of pain. So an important question for opiates is whether you can separate the rewarding and the analgesic components of pain. And the answer is we're not sure the answer to that question. I'm going to talk in a minute about the opioid receptors. The most important opioid receptors is called the mu opioid receptors. And you can make an animal where the mouse doesn't have this anymore. It does not have this particular receptor. So this is a knockout animal. And in this animal, if you look at these two experiments, which come from my friend Brigitte Kiefer, who made these animals, you see that in the normal animal, if you give morphine, you can see that these are different. So this morphine works. It blocks the tail withdrawal, the tail flick time, and makes it 8 seconds at this particular dose. But in the knockout animal, morphine has absolutely no effect. And if you look at the rewarding aspect, you see that that morphine works very well. And this is condition-place preference experiment that I just assigned. Morphine works very well in inducing reward, but in the knockout animal, this minus animal, it doesn't work. So in fact, we know that this particular mu receptor is important for both the reward and the analgesic, the pain-killing aspects of morphine. Now, quickly, I'm going to talk about a little bit of science. So I just mentioned the mu receptor. The mu receptor is the most important receptor, opioid receptor for pain, but it has more actions than just analgesic activity. It causes euphoria. We know that. That's why it's rewarding. Anybody who's ever taken an opiate probably has constipation. So it's constipating, and it kills you because of respiratory depression. Okay, so those are the most important aspects of what happens to you when you take a mu opiate. Now, I want to say at this point, all of the analgesics, all of the opiate analgesics on the market are all mu opioids. Okay, so they all have all of these actions. But in fact, that's not the whole story. There's actually three different opiate receptors. There's something called a mu, there's something called a delta, and there's something called a kappa. Now, these are all proteins that are found in the membranes of cells, and this is where the opioids bind. This is where morphine binds or heroin binds. It sticks to these receptors, and then something happens that leads to all of these different physiological actions. In fact, there are endogenous ligands that also bind to these receptors. Now, these are peptides. A peptide is a small protein, and these are found in the body, and they bind to the receptors themselves. Now, you've heard of these. These are endorphins. Endorphin is sort of a generic term for these opioid peptides. These come from three different families, three different proteins, and they bind somewhat selectively to these receptors. And this is important for ways that you can make non-addicting analgesics. Also important is that when binding to these receptors, you get different kinds of actions. So they're all analgesic, but binding to the delta receptor does not cause euphoria, nor does binding to the kappa receptor. In fact, delta receptor activation is antidepressant. Kappa receptor activation causes dysphoria, and I'm going to get to that in a minute. It also causes sedation and diuresis. So they have different actions when you bind to these different receptors. Now I'm going to talk about what happens when you bind to the receptor. And what happens is not necessarily the same. I've already talked about naloxone for a minute. Naloxone is an opioid antagonist. It binds to the receptor and it doesn't do anything. Okay? So what it actually does, it gets in the way. It gets in the way of the opioid binding. So it doesn't prevent it. So it prevents the opioid from having its actions. So whatever opioid effect you're measuring, an agonist or a full agonist has a maximal effect, and an antagonist has no effect whatsoever. But in fact, there are some compounds that are called partial agonists. As you can imagine, what happens is it binds and it only partially activates the receptor. And whatever effect you're happen to be measuring, it does it only partially. And you can see this. So this could be analgesic activity, or it could be some in vitro action. And so this type of compound, like buprenorphine, is only a partial agonist. And so it only activates some. Now the amount that it activates, in fact, is dependent upon the test, but buprenorphine is a partial agonist. So this is really what I came to talk about today, now that I'm almost done. And that is, how do you make a non-abused opiate? So theory number one was heroin. Just make some more opiates and try it out in people, but we can't do that anymore. So theory number two is make a partial mu agonist. Now, buprenorphine is an interesting compound. It's a very safe compound because of the fact that it's a partial agonist. And you can imagine that if this is respiratory depression that you're measuring, morphine will have a lot of respiratory depression because it's full agonist, but buprenorphine won't have as much. And in fact, it has what's called a ceiling effect. It doesn't have as much respiratory depression, and that's why it's safe. In fact, the same may go true for the reward. Okay, maybe it's not as addicting because it's only a partial agonist. In fact, this may be true. The problem is that it still has enough addiction liability. And we knew this right from the beginning. When buprenorphine was first being sold in England, it was started to be stolen out of pharmacies and out of medicine cabinets. So it was being stolen for a reason, and that's because it's addicting. Another theory for making a non-abusable analgesic is making a kappa agonist. So there was a compound CI named 977. In fact, there were a lot of kappa agonists that were tested in vitro and in animals and given to people, in fact. And these all fail because binding to the kappa receptor leads to dysphoria. It makes you feel bad. And nobody wants to feel bad when they're feeling bad. So taking this kind of a compound failed. Another idea is controlled release. OxyContin was one of those, but again, this failed. We know this is addicting. Another possibility is an agonist-antagonist. This is a very clever idea. So Suboxone is a combination of morphine, of I'm not sure what buprenorphine, I'm sorry. It's a combination of buprenorphine and naloxone. And the theory is that buprenorphine has a ceiling effect and naloxone doesn't. So if you start increasing the dose, you reach a point where the naloxone takes over and it's an antagonist. And so it blocks the actions of the buprenorphine. And this actually makes sense. So the theory is you can't get to such a high dose that it's going to be that rewarding or that it's going to kill you. And so this is a reasonable hypothesis, but it's still not used as an analgesic. It's still used only for drug abuse treatment. Another theory is that the slow pharmacokinetics may be less addictive. And this is possible. It works in animals. It's not clear that it works in people. And there's a company called Nectar, which made this compound that gets into the brain real slowly. And we know that heroin is really addictive because it gets in the brain really fast, and this gets in really slowly. But in fact, the problem with a compound like this is you are still addicted to the opiate. So you have to take this forever. It doesn't make the addiction go away. And so you'll still go through withdrawal. So this compound was just rejected by the FDA, and Nectar pulled it. You can have a peripherally acting compound. This may work. There's a compound in phase 3 clinical trials that may work. The problem is it's just not as potent as opioids, and it will not affect the emotional component of pain because this is a brain phenomenon. This is not a sensory peripheral phenomenon. So this is probably not going to be as successful as opioids. There's a company that is making an enkephalinase inhibitor. Enkephalin, remember, is the endogenous endorphin that is analgesic and binds to the opiate receptor. And this is in phase 1 clinical trials. So the trouble with enkephalin is that it's broken down very quickly. And if you can prolong its actions, you can increase the analgesic activity. And this does work in animals, and it's in phase 1 clinical trials in people. Another topic that is, let me give me another minute or two. Another topic that is important these days is called biased agonists. And there's a compound in clinical trials now that is used the theory of biased agonism. And I want to tell you very quickly how this works. And I hate the fact that I can't tell if anybody is out there chuckling, or in fact, if anybody's still there. But this is one of my favorite cartoons in the world. This is what people thought about opiate receptors 20 years ago. You bind to the receptor, and then something happens. Analgesia, euphoria, something happens. In fact, people know a lot more now. Once binding to the receptor, a lot of things happen inside the cell. There's all sorts of different pathways that are activated. And it's possible that analgesic activity can be separated by what the receptor, by which of these pathways the receptor is actually activating. And this is it in a more simplified form. This comes from a paper from Laura Bond, who's in Jupiter at Scripps Institute. And what it shows that there are two basic pathways that can be activated after the receptor is activated. And it's possible that if you can activate that one of these pathways, like here where it says G protein signaling affects the analgesic component of morphine, but this other pathway called beta-arrestin affects the reward pathway and the respiratory depression pathway. And if you can make a compound that activates the receptor differently so that it only activates one of these and not the two, you may come up with an analgesic that's non-addicting. Well, there's a lot of evidence now that that's not the case. And TRV-170, which has gone through phase 3 clinical trials, is just as addicting as morphine, and in fact didn't even help with the respiratory depression. So that didn't help either. One last thing that I'm going to talk about is this last one here, which is non-selective partial agonists. And here is where I have to tell you, you don't have to believe anything I say, because this is now an advertisement, because I am part of this company called Phoenix Pharma Labs that makes a compound called PPL-103. And PPL-103 is different because it activates all the receptors but it's a partial agonist at all three. And in fact, its highest efficacy, it activates kappa more than it does mu. And the ratio of activation of these is important. And so then what we have found at this point is that, that this compound is a potent analgesic, but in fact, if you look at reward in the conditioned place preference assay, it is not rewarding like morphine. It is not aversive like other kappa agonists. And in fact, if you look at self-administration, which is I show right here, this is a rat that's pushing a lever to self-administer the drug. You see that morphine is self-administered, but if you switch to PPL-103, it's not. So this is a different method of making a non-addicting analgesic. And our theory is that it activates both receptors in the appropriate ratio so that the kappa is not high enough to be aversive, the mu is not high enough to be rewarding, but there's enough mu to block the aversion of the kappa. And overall, it gets some kind of happy medium where you can get an analgesic that is neither rewarding nor aversive and may be useful as an analgesic. As I said, we're now prior to clinical trials. Hopefully that will happen in the next year. We have hopes for this as something that can really help people. And I have the conclusion, and I'm not going to talk about it because I've already said all of these things, but basically there are a lot of different methods. Biased agonism has not failed. It's still an important potential mechanism for work as all the others that I talked about. And hopefully non-addicting analgesics are on the horizon. Thank you very much. I'm sorry that you couldn't ask questions then, but go for it now, please. Karen, are you there?
I'm here. Thanks, Larry. Okay, thank you very much. Pardon?
Is anybody else still there?
Yep, anybody else is still there. So we have a few minutes to go over questions. If you have any questions, please use the Q&A button in the bottom of your screen. And I will go through them and moderate them since we won't allow audio questions. I also wanted to mention that this will be recorded. And the link for the recording will be up on our Research in Action website at the FAU Division of Research site in a day or two. So if you would like to see this again. Okay, Larry, here's your first question. Can you speak a little bit about the side effects of an opioid drug on the rest of your body aside from the addiction that it causes? What else are the side effects of these opioid drugs?
Right, so I did mention it. So most of the drugs, all of the drugs you've ever taken are mu opioids, and they cause respiratory depression. That's why you die. They cause constipation. My uncle had a heart surgery, and he said, "Oh, the constipation killed me. It was worse than the addiction, or worse than everything else." So it causes constipation, respiratory depression. It's antidiuretic. So there's a bunch of other things that it causes. That are quite serious side effects. In fact, for a long time, doctors were much more worried about the constipation than the addiction liability, and NIDA is more worried about the respiratory depression because that's what kills you. So clearly there are side effects.
Yeah. An interesting question is related to the different compounds that have been created over time. You mentioned them. How do researchers choose which chemical parts of the compounds to change?
Well, I am not a medicinal chemist. I am a pharmacologist, but I have worked with medicinal chemists forever, for many, many years, and they're very good at this. And the technique has changed over the years. In fact, it's become much more sophisticated. It used to be that chemists can tell what parts of the molecule can be changed, okay? And so they'll make modifications there and see what happens. And you can make changes in different ways. You can make something that's charged or something that's lipophilic. That means it's like fat. So you can do this on certain parts of the molecule. And then you see if it makes any effect. And then you do it on another part of the molecule and you see what makes any effect. And so you can change all these different parts of the molecule and see what happens. It turns out it's become much more sophisticated in the more recent past using the molecular modeling, which allows you to see how the molecule really sits in 3 dimensions. And so medicinal chemists are now all the time use molecular modeling to see what type of a change in what part would cause what kind of a change to the whole molecule itself. And it's become more sophisticated since then, because in fact, there is a technique called X-ray crystallography, and I showed you a picture of the new receptor. And with X-ray crystallography, you can actually see the 3-dimensional structure of the receptor itself. And so now with molecular modeling, you can do docking of the molecule itself. So they take the molecule and they dock it in situ, not in situ, in silico into the receptor itself. And they can see what parts of the molecule fit within the receptor. And then they end up making those compounds, and that speeds up the process. So it's gotten really sophisticated, and basically I have no idea what I'm talking about.
A really interesting question on addictive personalities. Is it true or false that 2 different people can get the same prescription drugs for the same amount of time? And if one has a genetic predisposition to addiction, they would have a harder time to discontinue the use?
Absolutely. In fact, I used to collaborate with a guy when I was in California who did twin studies. He studied more nicotine than opiates, but from these type of studies, you can tell that addiction is approximately 50% hereditary. So if you have it in your family, you should be careful, because you are going to be more likely to become addicted than somebody else, and it's just the luck of the draw, I'll tell you. And so this is very important, and this is something you should keep in mind.
What are the symptoms for withdrawal from opioids? You mentioned some of them earlier.
Yeah, I'm not sure what they all are. In people, I'm not a physician, and I have never gone through this myself and don't plan on. But I know they're terrible stomach problems and physical withdrawal that you don't see with most other things. Withdrawal from most things is more psychological. There's depression and there's anxiety. And if you stop smoking, it's not so bad. You can go through withdrawal. Smokers do it most every day, and everybody's tried to quit, and it's not so bad. But for morphine opiate withdrawal, it's very, very severe. And so blocking the withdrawal with things like clonidine really makes a difference in trying to quit. But I'm not an expert on that. I'm not positive.
Okay. Is the goal of the PPL 103 to be a first-line treatment for a pain, acute or chronic, or as a response to an already addicted user as a means to reduce harm?
We would like it to be a first-line drug. It depends on how it ends up when given into people. We don't know yet. We're also looking into it as a drug abuse medication, in fact, because it could be used in theory like something like methadone, because actually it blocks withdrawal from opiates, at least it does in rats. So it could be used as an abuse medication as well. In fact, we've done studies. It blocks cocaine self-administration as well, for a different reason, because it's a kappa drug. So we see it as a potential drug abuse medication. But first line, what it's being developed for now is pain as a first line drug.
Great. Okay, we have time for one more question. The remaining questions we will gather and ask Dr. Toll to answer, and we will post the answers on our website. The last question I'm going to actually partially answer myself, because it is if there is enough research money to move towards changing the addiction and the death as in the American crisis. And I can tell you from my standpoint, there's never enough money for research. That's actually what our office here is supporting and trying to get funding for any of our research. Any of it is important in its own right. But Larry, maybe you want to speak about that as well.
I'm not going to disagree with you, Karen. My lab never has enough money to do research, so there you go. But so the government threw a lot of money in it last year and the year before, a lot of money. And so that did help. But now that's all going to COVID-19 instead. And that's important too.
Yeah.
COVID-19 will go away, drug abuse won't. And identifying analgesics is a long-term process. So no, there's not enough money. There's always can be more. I mean, from a scientist's point of view, yeah, there's never enough money.
Yeah, and you know, if you have the ability to help, just contact us. We'd be happy to talk with you about that for sure. With that, I'm going to thank you, Larry. We will be answering the remaining questions. I see there are more questions. So please look on our website. It will be up in a few days, as well as the recording of this presentation.
All right.
We thank you.
Yes, and
thanks, Larry.
14 people who are still there. I do appreciate it.
Great. Thanks so much. Hope to see you soon again. Bye-bye.